everyone, my name is Juliana and I'm doing my PhD at Memorial University of Newfoundland in St. John's. In this presentation, I'll be talking about the investigation I've been performing with my supervisor, Dr. Francesca Curtin, and my co-supervisor, Dr. Stephanie McCoy, in using Biochar as a Nexus solution for the achievement of a bioeconomy. Our story starts in the middle of the woods during the production of wood materials from sawed, lumber, and paper mill industries. When these industries use the parts of the trees they need, the waste is usually transported to landfills or left aside to decompose. The problem with the decomposition of this biomass residue is that it releases greenhouse gases to our atmosphere. There's a process, however, known as pyrolysis that can help to mitigate this release. So during pyrolysis, waste biomass from trees or even from agricultural residues is burned under low conditions of oxygen and transformed into biochar, a carbon material that decomposes way more slowly. So therefore, pyrolysis is able to reroute carbon from a rapid biological cycle into a much slower cycle promoted by the production of biochar. Bio-oil and syngas are also co-produced during this process, and they can be further used as a source of renewable energy to feed the pyrolysis reactor. In terms of its structure, biochar is a material that presents porosity, surface functionality, and also surface area, but it is mainly used in low value added fields such as a pollutant removal and also as a soil amendment. In our research, we've been looking into different strategies to actually improve the biochar applications. So the first one consists in the investigation of oxidized biochar as a catalyst to produce cyclic carbonates, which are compounds used industrially. So by using oxidized biochar as a catalyst for the cycloaddition reaction between CO2 and epoxides, we could produce a material that sequesters CO2 during its production to further apply as a catalyst for a process that transforms CO2 into cyclic carbonates. And by doing that, we could help to mitigate climate change effects while we synthesize useful compounds. So during our studies, we found out that oxidized biochar could facilitate the reaction via hydrogen bonding, that biochars from different biomass feedstocks could be used to promote the reaction under mild reaction conditions, that a wide range of substrates could work for a catalytic system, and also that oxidized biochar could be reused for at least 5 times, being a sustainable, renewable, efficient, and also recyclable catalyst for the cycloaddition reaction between CO2 and epoxides. So the other strategy that we considered was the increase of biochar applications via a process known as liquid phase exfoliation, or LPE for short. So during LPE, the layered material is immersed in a solvent and its weak interaction between layers are broken using ultrasound to produce nanosheets containing enhanced chemical and physical properties. So we wanted to study the applications of nanostructures of biochar, but we found out that it has been previously done in a toxic solvent to human health and the environment. So we took a step back and decided if we could perform the LPE in greener solvents before studying the applications of the exfoliated material. So in the second investigation, we were able to correlate exfoliation efficiency with the densities, surface tensions, and also the Campbell-Taft parameters of the solvents used. We could produce biochar nanosheets with 15 nanometers thickness in solvents such as solketal, ethyl acetate, and also dimethyl carbonate, whereas oxidized biochar could be exfoliated in solvents such as polyethylene glycols and caprolactone. And we also could exfoliate samples for at least 2 hours without any loss in their quality. So in summary, we have applied 2 different strategies so far for the diversification of biochar applications, but we believe that this is only the beginning. By applying carbon material that is obtained from waste for the production of advanced materials, we can produce industrially used chemicals, and help to boost the whole bioeconomy concept through the transformation of waste into something valuable. So we believe that this is key and a very important piece for our achievement to a truly sustainable future. So with that, I would like to thank all of the people involved in this project, my supervisor, my co-supervisor, and the organizers of the Atlantic BIOCON for this wonderful conference. And also thank you all very much for your attention. Thank you.